Hi everyone, my name is Neha and this is the 10th lecture on Introduction to Automation. In this lecture, we are going to learn about the temperature sensors. Temperature sensors, they give an output proportional to temperature, and most of the temperature sensors, they have positive temperature coefficient, and some of the sensors, they have negative temperature coefficient. Now what does that mean? It means in positive temperature coefficient, when the temperature increases, the sensor output also increases. Whereas in negative temperature coefficient, as the temperature increases, the sensor output goes down. Now we're gonna see some of the common types of temperature sensors. First, bimetallic temperature sensors. Second, thermocouples. Third, resistance temperature detectors. Fourth, thermistors. Bimetallic temperature sensor, it converts temperature to a mechanical displacement, and that mechanical displacement may be coupled to a switch for simple on-off function, or to a needle of an indicator, or to a position detector for any electronic output. These temperature sensors, they are used in thermostat switches, used for temperature and energy control measurement. And let's see the construction of the bimetallic temperature sensor. It consists of two metals, metal A and another is metal B. And these two metals, they have different thermal off coefficient. And here you see a globe of mercury which is attached over here, and at the end is your mercury switch. So what happens when the temperature increases, then this mercury globe of mercury, it rotates clockwise when tube rotates past the horizontal, and then the mercury runs down to the right and completes the electrical connection between the electrodes. So that's how it works, and at the output here you can connect any electronic component, for example position detector or any indicator or a simple on-off switch you can connect, which will respond corresponding to the change in the temperature. Now this bimetallic temperature sensor, it has some advantages also. In this type, you do not need to have the signal conditioning equipment. The output can be directly used without any change. Now here on the right you see this is the another example of the picture of bimetallic temperature sensor, and these are the two different metals which are used, and here is the electrical connection, and you see here the contact of electrical contact. Right now this bimetallic strip is in contact with the electrical connection, and as the heat is you can see here in the other picture, as the heat is increased, then this bimetallic strip, it will go up and it will open up the contact with this terminal. On the right you see here a bimetallic temperature sensor, and that's how it looks like, and through this scale you can measure the change in the temperature. Now next we have thermocouple. Thermocouple is based on the Seebeck effect, and it is a phenomena where whereby a voltage that is proportional to the temperature can be produced from a circuit which consists of two dissimilar metal wires. So this thermocouple, it consists of two different types of metals which are joined together at one end, and when the junction of the two metals you see here is heated or cooled, a voltage is created and that can be correlated back to the temperature. Now here one junction is called as a hot junction, and other junction is kept at some reference temperature, and it is called a cold junction, or we can say a reference junction. Now from here, center portion, you see from here the net voltage is basically calculated based on the two voltages created due to hot and the cold junction. And here you see the another picture of a thermocouple where when the temperature is increased or heat is provided at the hot junction, and this is our reference junction which is the cold junction, then and these are the two wires, Then when this hot junction is fired, and as it is fired, the temperature will increase, and when the temperature increases, then there will be a net change in the voltage, and that net change can be calculated through this voltage net. And here you see voltmeter is attached here, and through this voltmeter we can measure the change in temperature in terms of voltage. Now the output voltage from this system can be expressed by this equation: V net is equals to V hot minus V cold, and this V hot can be put over here, and we can rewrite this equation in this form, where this V cold, this is the constant, this V cold, it can be at 32 degree Fahrenheit or some other reference temperature according to our application of the system. Now, traditionally, the reference temperature, which is the cold voltage, let's go back here. So this constant RV cold at 32 degree Fahrenheit, which is at reference temperature, this used to be maintained at this constant voltage by using the ice water bucket. But the modern system has eliminated that use, and it has come up with different solutions. First is maintaining the cold junction at constant temperature with using some control system. Second is simply look up in a table by using the computer controller, and you can look up the value of V cold for the ambient temperature and add that value to the V net to get the value of V hot. Next, we have use of temperature sensitive diode. You can see here, this is the temperature sensitive diode, and it is used in an interface circuit with the thermocouple, and an op amp is attached here, and from this we get the output voltage. So this thermocouple, its output behaves as if the cold junction were still at a freezing temperature, even though it's not, with the help of this diode, this temperature sensitive diode. So what happens in this, as the ambient temperature around the cold junction, as it varies, then the thermal voltage will be generated, and that thermal voltage will produce an error in the output. So here an equal automatic equal and opposite voltage will be produced in series with the thermal error, and this cancels the error and maintains the equivalent reference junction temperature over a wide ambient temperature range with a high degree of accuracy. So that's how it works, and on the right you see the graph between the temperature in Fahrenheit and the thermocouple output in millivolts. And you see here, for it is the graph is shown for three different metal wires. First is the iron constantan, and next is the chromel aluminum, and third is the platinum pure platinum 13% rhodium. So here this J, it has, you can see based on its graph that it has high sensitivity, and but it has a lowest temperature range. And then next this K, chromel aluminum, it has high temperature range but low sensitivity. And the third one, which is the platinum pure platinum, it has lower sensitivity but it can work at a high frequency. You can see here the frequency range is higher for this metal wire. Now next we have resistance temperature detectors. The resistance temperature detector, it is a temperature sensor based on the fact that the metals increase in resistance as temperature rises. So these resistance temperature detectors, it is a thin film made up of platinum, which is used for measurement of temperature. And these detectors, they have a great stability, accuracy and repeatability. The resistance of this type of detector, it tends to be almost linear with the temperature, which means as the temperature increases, the resistance also increases linearly. So here you see this, inside this you have this platinum wire which is wrapped around a ceramic or a glass rod, and sometimes wire is supported between the two ceramic rods. So in the resistance temperature detectors, the platinum wire which it has a temperature coefficient of 0.0039 ohm per degree centigrade. So which means that for each degree Celsius, the resistance goes up by this amount, which is 0.0039 ohm. And these resistance temperature detectors, they are available in different resistance, and the common value are usually around 100 ohm. And on the right you see this is the picture of a resistance temperature detector, and that's how it looks like. Now next we have thermistor, and thermistor, it is a two-terminal device that changes resistance with temperature. And a thermistor, they are made up of oxide-based semiconductor materials, and which comes in variety of shapes and sizes. So here you see this is one of the thermistor which has been shown in this picture. And these thermistors, they are non-linear, and you can see that through this graph which is shown between the resistance and the temperature. And you can see this is how the graph will look like for resistance versus temperature, and you see this is a non-linear graph. Therefore we can say that they are not usually used to get accurate temperature reading. And on the right you see this is an interface circuit where this is the thermistor is connected with this resistance, and from here you get the output voltage. So in general, all thermistor, they have negative temperature coefficient, and you can easily get it from this graph. As you can see, when the resistance increases, the temperature decreases, or you can say as the resistance decreases, the temperature increases. Now here, the desirable feature of a thermistor is that its sensitivity, which is high, which means that with a small change in the temperature, it can result in a large change in the resistance. And if we see this interface circuit here, you see that thermistor is placed over on top of the resistance, or you can say this is a voltage divider. This is forming like a voltage divider, and you're getting the output voltage corresponding to this ground. So you see here that it will have this type of arrangement. It will have a linear output voltage, and it will have a positive slope, and that you can see over here in this graph, that this type of curve you will obtain if you put the thermistor in the voltage divider circuit, or in this type of interface circuit. So if the voltage looks like this, then what does it mean? It means that your resistance will vary linearly with the temperature. Now this is another integrated circuit of the temperature sensor, and here this thermistor is used, which is LM35, and the output voltage of this LM35 thermistor is going to be directly proportional to the degree centigrade, which is the temperature. And for this particular circuit, it is going to be output voltage is going to be 10 millivolts per degree centigrade. So the integrated circuit for temperature sensor, it comes in various configuration, and the example which you see here is the common type of interface circuit which has been used. And in this one you see that the output voltage which is going to be produced, it is going to be in proportional with the change in the temperature, and that's how this interface circuit will look like. Let's see this problem based on temperature sensor. It says an iron constant and thermocouple is used to measure the temperature in an oven. The cold junction, it is at a ambient temperature of 80 degree Fahrenheit, and the thermocouple voltage is at 12 millivolts. What is the approximate oven temperature? So this ambient temperature of 80 degree Fahrenheit you see here, it is your reference temperature value. And the voltage which you see here, thermocouple voltage, is 12 millivolts. This is your V hot voltage, so hot junction voltage we can say. In this one we have to find the oven temperature. We will be first using up the net voltage formula, and then we will calculate the corresponding temperature. So the first thing we need to do is to convert this degree Fahrenheit into the voltage, and that can be done by using this graph you see over here. So in this graph, a search for 80 degree Fahrenheit. You see that 80 degree Fahrenheit is going to be a very small value, because here you see the first we see here in this horizontal axis is the 500. So 80 degree Fahrenheit is going to be somewhere here close to here. So let's see what the voltage of 80 degree Fahrenheit is. So approximately value which you'll get based on this graph is going to be 1.5 millivolts. And once you know this value, then you can calculate the V net voltage. So V net voltage is by formula is equals to V hot plus V cold. So this is the V cold voltage, you will put it out here, and V hot voltage we already know in the problem, and it is 12 millivolts. So V net you will get 13.5 millivolts. So this is the voltage you got, but you have to find out the approximate oven temperature. And to find the oven temperature, you will again look up in the graph, and corresponding to 13.5 volts millivolts, you will look for the temperature here, and you will get around maybe something like 300 degree Fahrenheit. Now let's see another problem. It says 100 ohm platinum RTD is being used in a system. The present resistance reading is 130 ohm. Find the temperature. Now here you need to note down that 100 ohm platinum RTD, it has a resistance of this at 0 degrees centigrade, and it has a positive temperature coefficient of this value. So based on the problem, we see that 30 ohm resistance has been increased, or we can say has gone up from 100 ohm, because now it is 130. So if we take the difference, then we find that the 30 ohm resistance has gone up. So let's see how you are going to calculate that. So using that 30 ohm, you will put in this formula, and you can get the temperature, which is 77 degrees centigrade. So this temperature value shows that the temperature for this present resistance. So this is the end of the lecture. Thank you so much for watching.